In differential geometry, representation theory and harmonic analysis, a symmetric space is a smooth manifold whose group of symmetries contains an inversion symmetry about every point. There are two ways to formulate the inversion symmetry: via Riemannian geometry or via Lie theory. The Lie theoretic definition is more general and more algebraic. In Riemannian geometry, the inversions are geodesic symmetries, and these are required to be isometries, leading to the notion of a Riemannian symmetric space. More generally, in Lie theory, a symmetric space is a homogeneous space G, H for a Lie group G such that the stabilizer H of a point is an open subgroup of the fixed point set of an involution of G. This definition includes Riemannian symmetric spaces and pseudo-Riemannian symmetric spaces as special cases. Riemannian symmetric spaces arise in a wide variety of situations in both mathematics and physics. They were first studied extensively and classified by Ehrlich. More generally, classifications of irreducible and semi-simple symmetric spaces have been given by Marcel Berger. They are important in representation theory and harmonic analysis as well as differential geometry. Definition using geodesic symmetries. Let M be a connected Riemannian manifold and P a point of M. A map F defined on a neighborhood of P is said to be a geodesic symmetry if it fixes the point P and reverses geodesics through that point, i.e., if gamma is a geodesic and then it follows that the derivative of the map at P is minus the identity map on the tangent space of P. On a general Riemannian manifold, F need not be isometric, nor can it be extended, in general, from a neighborhood of P to all of M. M is said to be locally Riemannian symmetric if its geodesic symmetries are in fact isometric, and Riemannian symmetric if in addition its geodesic symmetries are defined on all of M. Basic properties. The Cartan-Ambrose-Higgs theorem implies that M is locally Riemannian symmetric if and only if its curvature tensor is covariantly constant, and furthermore that any simply connected, complete locally Riemannian symmetric space is actually Riemannian symmetric. Any Riemannian symmetric space M is complete and Riemannian homogeneous. In fact, already the identity component of the isometry group acts transitively on M. Locally Riemannian symmetric spaces that are not Riemannian symmetric may be constructed as quotients of Riemannian symmetric spaces by discrete groups of isometries with no fixed points, and as open subsets of Riemannian symmetric spaces. Examples. Basic examples of Riemannian symmetric spaces are Euclidean space, spheres, projective spaces, and hyperbolic spaces, each with their standard Riemannian metrics. More examples are provided by compact, semi-simple Lie groups equipped with a bi-invariant Riemannian metric. An example of a non-Riemannian symmetric space is anti-de Sitter space. Any compact Riemann surface, a genus greater than 1, is a locally symmetric space but not a symmetric space. General definition. Let G be a connected Lie group. Then a symmetric space for G is a homogeneous space G, H where the stabilizer H of a typical point is an open subgroup of the fixed point set of an involution sigma in AUT. Thus sigma is an automorphism of G with sigma 2 equals IDG, and H is an open subgroup of the set because H is open. It is a union of components of G sigma. As an automorphism of G, sigma fixes the identity element, and hence, by differentiating at the identity, it induces an automorphism of the Lie algebra of G, also denoted by sigma, whose square is the identity. It follows that the eigenvalues of sigma are plus or minus 1. The plus 1 eigenspace is the Lie algebra of H, and the minus 1 eigenspace will be denoted. Since sigma is an automorphism of, this gives a direct sum decomposition with the first condition is automatic for any homogeneous space. It just says the infinitesimal stabilizer is a Lie subalgebra of. The second condition means that is an invariant complement to in. Thus any symmetric space is a reductive homogeneous space, but there are many reductive homogeneous spaces which are not symmetric spaces. The key feature of symmetric spaces is the third condition that brackets into. Conversely, given any Lie algebra with a direct sum decomposition satisfying these three conditions, the linear map sigma equal to the identity on and minus the identity on is an involutive automorphism. Riemannian symmetric spaces are symmetric spaces. If M is a Riemannian symmetric space, the identity component G of the isometry group of M is a Lie group acting transitively on M. Therefore, if we fix some point P of M, M is diffeomorphic to the quotient G, K, where K denotes the isotropy group of the action of G on M at P. By differentiating the action at P we obtain an isometric action of K on TPM. This action is faithful and so K is a subgroup of the orthogonal group of TPM, hence compact. Moreover, if we denote by SP, MM the geodesic symmetry of M at P, the map is an involutive Lie group automorphism such that the isotropy group K is contained between the fixed point group of sigma and its identity component. To summarize, M is a symmetric space G, K with a compact isotropy group K. Conversely, symmetric spaces with compact isotropy group are Riemannian symmetric spaces, although not necessarily in a unique way. To obtain a Riemannian symmetric space structure we need to fix a K invariant inner products on the tangent space to G, K at the identity coset ek. Such an inner product always exists by averaging, since K is compact, and by acting with G, we obtain a G-invariant Riemannian metric G on G, K. To show that G, K is Riemannian symmetric, consider any point P equals HK and define where sigma is the involution of G fixing K. Then one can check that SP is an isometry with SP equals P and DSP equal to minus the identity on TPM. Thus SP is a geodesic symmetry and, since P was arbitrary, M is a Riemannian symmetric space. If one starts with a Riemannian symmetric space M, and then performs these two constructions in sequence, then the Riemannian symmetric space yielded is isometric to the original one. This shows that the algebraic data completely describe the structure of M. Classification of Riemannian symmetric spaces. The algebraic description of Riemannian symmetric spaces enabled Elie Cartan to obtain a complete classification of them in 1926. For a given Riemannian symmetric space M, let be the algebraic data associated to it. To classify possibly isometry classes of M, first note that the universal cover of a Riemannian symmetric space is again Riemannian symmetric, and the covering map is described by dividing the connected isometry group G of the covering by a subgroup of its center. Therefore, we may suppose without loss of generality that M is simply connected. Classification scheme: a simply connected Riemannian symmetric space is said to be irreducible if it is not the product of two or more Riemannian symmetric spaces. It can then be shown that any simply connected Riemannian symmetric space is a Riemannian product of irreducible ones. Therefore, we may further restrict ourselves to classifying the irreducible, simply connected Riemannian symmetric spaces. The next step is to show that any irreducible, simply connected Riemannian symmetric space M is of one of the following three types. 1. Euclidean type. M has vanishing curvature, and is therefore isometric to a Euclidean space. 2. Compact type. M has non-negative sectional curvature. 3. Non-compact type. M has non-positive sectional curvature. A more refined invariant is the rank, which is the maximum dimension of a subspace of the tangent space on which the curvature is identically zero. The rank is always at least 1, with equality if the sectional curvature is positive or negative. If the curvature is positive, the space is of compact type, and if negative, it is of non-compact type. The spaces of Euclidean type have rank equal to their dimension and are isometric to a Euclidean space of that dimension. Therefore, it remains to classify the irreducible, simply connected Riemannian symmetric spaces of compact and non-compact type. In both cases there are two classes. A. G is a simple Lie group. B. G is either the product of a compact simple Lie group with itself, or a complexification of such a Lie group. The examples in Class B are completely described by the classification of simple Lie groups. For compact type, M is a compact simply connected simple Lie group, G is M times M and K is the diagonal subgroup. For non-compact type, G is a simply connected complex simple Lie group and K is its maximal compact subgroup. In both cases, the rank is the rank of G. The compact simply connected Lie groups are the universal covers of the classical Lie groups, and the 5 exceptional Lie groups E6, E7, E8, F4, G2. The examples of Class A are completely described by the classification of non-compact simply connected real simple Lie groups. For non-compact type, G is such a group and K is its maximal compact subgroup. Each such example has a corresponding example of compact type. By considering a maximal compact subgroup of the complexification of G which contains K, more directly, the examples of compact type are classified by involutive automorphisms of compact simply connected simple Lie groups G. Such involutions extend to involutions of the complexification of G, and these in turn classify non-compact real forms of G. In both Class A and Class B there is thus a correspondence between symmetric spaces of compact type and non-compact type. This is known as duality for Riemannian symmetric spaces. Classification results specializing to the Riemannian symmetric spaces of Class A and compact type. Cartan found that there are the following 7 infinite series and 12 exceptional Riemannian symmetric spaces G, K. They are here given in terms of G and K, together with a geometric interpretation, if readily available. The labeling of these spaces is the one given by Cartan. As Grassmannian's a more modern classification uniformly classifies the Riemannian symmetric spaces, both compact and non-compact, via a Freudenthal magic square construction. The irreducible compact Riemannian symmetric spaces are, up to finite covers, either a compact simple Lie group, a Grassmannian, a Lagrangian Grassmannian, or a double Lagrangian Grassmannian of subspaces of four-normed division algebras A and B. A similar construction produces the irreducible non-compact Riemannian symmetric spaces. Symmetric spaces in general. An important class of symmetric spaces generalizing the Riemannian symmetric spaces are pseudo-Riemannian symmetric spaces, in which the Riemannian metric is replaced by a pseudo-Riemannian metric. In particular, Lorentzian symmetric spaces, i.e., n-dimensional pseudo-Riemannian symmetric spaces of signature, are important in general relativity, the most notable examples being Minkowski space, de Sitter space and anti-de Sitter space. The Sitter space of dimension n may be identified with the one-sheeted hyperboloid in a Minkowski space of dimension n plus 1. Symmetric and locally symmetric spaces in general can be regarded as affine symmetric spaces. If M equals G, H is a symmetric space, then Nomizu showed that there is a G-invariant torsion-free affine connection on M whose curvature is parallel. Conversely, a manifold with such a connection is locally symmetric. Such manifolds can also be described as those affine manifolds whose geodesic symmetries are all globally defined affine diffeomorphisms, generalizing the Riemannian and pseudo-Riemannian case. classification results. The classification of Riemannian symmetric spaces does not extend readily to the general case for the simple reason that there is no general splitting of a symmetric space into a product of irreducibles. Here a symmetric space G H with Lie algebra is said to be irreducible if is an irreducible representation of. Since is not semi-simple in general, it can have indecomposable representations which are not irreducible. However, the irreducible symmetric spaces can be classified. As shown by Katsumi Nemizu, there is a dichotomy. An irreducible symmetric space G H is either flat or is semi-simple. This is the analog of the Riemannian dichotomy between Euclidean spaces and those of compact or non-compact type, and it motivated M. Berger to classify semi-simple symmetric spaces and determine which of these are irreducible. The latter question is more subtle than in the Riemannian case. Even if it's simple, G H might not be irreducible. As in the Riemannian case, there are semi-simple symmetric spaces with G equals H times H. Any semi-simple symmetric space is a product of symmetric spaces of this form with symmetric spaces such that is simple. It remains to describe the latter case. For this, one needs to classify involutions sigma of a simple Lie algebra. If is not simple, then is a complex simple Lie algebra, and the corresponding symmetric spaces have the form G H, where H is a real form of G. These are the analogues of the Riemannian symmetric spaces G, K with G a complex simple Lie group, and K a maximal compact subgroup. Thus we may assume is simple. The real subalgebra may be viewed as the fixed point set of a complex antilinear involution tau of, while sigma extends to a complex antilinear involution of commuting with tau and hence also a complex linear involution sigma tau. The classification therefore reduces to the classification of commuting pairs of antilinear involutions of a complex Lie algebra. The composite sigma tau determines a complex symmetric space, while tau determines a real form. From this it is easy to construct tables of symmetric spaces for any given, and furthermore, there is an obvious duality given by exchanging sigma and tau. This extends the compact, non-compact duality from the Riemannian case, where either sigma or tau is a Cartan involution, i.e., its fixed point set is a maximal compact subalgebra. Tables. The following table indexes the real symmetric spaces by complex symmetric spaces and real forms, for each classical and exceptional complex simple Lie group. For exceptional simple Lie groups, the Riemannian case is included explicitly below, by allowing sigma to be the identity involution. In the above tables this is implicitly covered by the case KL equals 0. Weakly symmetric Riemannian spaces. In the 1950s A.T.L.E. Selberg extended Cartan's definition of symmetric space to that of weakly symmetric Riemannian space, or in current terminology weakly symmetric space. These are defined as Riemannian manifolds M with a transitive connected Lie group of isometries G and an isometry sigma normalizing G such that given X, Y and M there is an isometry S in G such that Sx equals sigma Y and psi equals sigma X. Selberg proved that weakly symmetric spaces give rise to Gelfand pairs, so that in particular the unitary representation of G on L2 is multiplicity-free. Selberg's definition can also be phrased equivalently in terms of a generalization of geodesic symmetry. It is required that for every point x in M and tangent vector x at x, there is an isometry S of M, depending on x and x, such that S fixes x. The derivative of S at x sends x to x. When S is independent of X, M is a symmetric space. An account of weakly symmetric spaces and their classification by Akiza and Wimberg, based on the classification of periodic automorphisms of complex semi-simple Lie algebras, is given in Wolf, Applications and Special Cases. Symmetric spaces and holonomy. If the identity component of the holonomy group of a Riemannian manifold at her point acts irreducibly on the tangent space, then either the manifold is a locally Riemannian symmetric space, or it is in one of 7 families. Hermitian symmetric space is a Riemannian symmetric space which is additionally equipped with a parallel complex structure compatible with the Riemannian metric is called a Hermitian symmetric space. Some examples are complex vector spaces and complex projective spaces, both with their usual Riemannian metric, and the complex unit balls with suitable metrics so that they become complete and Riemannian symmetric. An irreducible symmetric space G, K is Hermitian if and only if K contains a central circle. A quarter turn by this circle acts as multiplication by I on the tangent space at the identity coset. Thus the Hermitian symmetric spaces are easily read off of the classification. In both the compact and the non-compact cases it turns out that there are 4 infinite series, namely AIII, BDI with P equals 2, DIII and CI, and 2 exceptional spaces, namely EIII and EVII. The non-compact Hermitian symmetric spaces can be realized as bounded symmetric domains in complex vector spaces. Quaternion Kähler symmetric space is a Riemannian symmetric space which is additionally equipped with a parallel subbundle of end-isomorph vector, imaginary quaternions at each point, and compatible with the Riemannian metric, is called Quaternion Kähler symmetric space. An irreducible symmetric space G, K is quaternion Kähler if and only if isotropy representation of K contains an SP summand acting like the unit quaternions on a quaternionic vector space. Thus the quaternion Kähler symmetric spaces are easily read off from the classification. In both the compact and the non-compact cases it turns out that there is exactly one for each complex simple Lie group, namely AI with P equals 2 or Q equals 2, BDI with P equals 4 or Q equals 4, CII with P equals 1 or Q equals 1, EII, EV, EIX, Phi and G. Bott periodicity theorem. In the Bott periodicity theorem, the loop spaces of the stable orthogonal group can be interpreted as reductive symmetric spaces.